Welcome to another exciting video brought to you by Chrysolite Tutors. We'll be looking at Physics 121, Electricity, Magnetism and Modern Physics. And we're starting off with Unit 1, Electric Charge, Force and Field. In this particular video, we'll look at the difference between the two kinds of charge, the positive and negative electric charge. We also show that the total electric charge in an isolated system is conserved, state Coulomb's law, and use it to find the electrostatic force between two charges. We also state the superposition principle, calculate the vector sum of the electric field due to a number of point charges, and finally we'll sketch the field lines for some simple distribution of charge. So stay tuned to the end of this video to enjoy all what we have for you. If you're not subscribed to the channel, kindly subscribe, like, and comment. Share with your friends so that they can see this video. Now, have you ever wondered about lightning and thunder? There are two common phenomena in our hot and humid atmosphere in Nigeria. Have you ever given a thought what is responsible to this occurrence or phenomenon? So Benjamin Franklin is a physicist. He demonstrated long ago in 1752 that thunder clouds are charged with electricity. So that is the concept of the charge that we'll be looking at. There are two types of charge. You have the positive charge, positive, and the negative charge, negative. So the nature of these charges is that this one has more of positive ions on it, and this has more of negative ions on it. So two positive charges, like charges, let's say like charges attract. Like charges attract. This is the hallmark of like charges. They attract. So if I have positive and positive, these are like charges. They are the same. And negative, they attract. So the force of attraction makes the vector to go this way. So they tend to come together. A force pulls them together. So secondly, number one. Secondly, number two, unlike charges repel. Unlike charges repel. So there's a force that tries to take the unlike charges away from each other. So this is repulsion this way, this way. This is force F1 and F2. So if it is unlike charges, so positive and negative, so they repel. So that is what you have. So actually a scientist came to study the nature of these charges. We'll look at it in a short while, Coulomb, and it was a law that he introduced to study the force, the force of attraction. But before we go to that law, this charge Q, the charge is denoted as Q, is also expressed mathematically as IT, where I is the current measured in amperes, and T is the time measured in seconds. So these are SI units for these two parameters. Already Q, quantity of charge, is measured in coulombs. Okay. So these are the units of the charge that we have. So before we dive into Coulomb's law, I would like to state that the charge conservation law states as follows. It states that the total electric charge in an isolated system, that is the algebraic sum of the positive and negative charge present at any time, does not change. It does not change. So but Coulomb came to study the force of attraction between these two charges. It states that the force of attraction or repulsion, F, is directly proportional to the product of the charges. So if I have two charges interacting in the electric field, understand? Coulomb's law says that the force of attraction between these two charges is directly proportional to the product of the charge. Remember, charge measured in Coulomb. At the same time, is inversely proportional to the square of the distance of separation. Okay, so if I remove the constant proportionality constant here, and I introduce, the sign, proportionality sign here, and I introduce k. So I have F is equals to k, Q1 Q2 over R squared. Now, what is all these parameters? Let's define them. F is defined as the force of attraction or repulsion, as the case may be, measured in Newton. K is the proportionality constant of proportionality, and K actually is 1 over 4 pi epsilon naught. Now, another thing has been introduced here. Epsilon naught is known as permittivity of free space. Permittivity of free space. I will talk about it in a short while. Permittivity of free space. Okay. Now, Q1 and Q2, Q1, Q2 are quantity of charge or charges measured in Coulomb. So the Coulomb is the unit of charge. Remember that. And R is the distance of separation. Distance of separation between the two charges. Distance of separation. So these are the parameters involved in this formula for Coulomb law. We'll be looking at it in a short while to dissect what it's all about. Now, let me just throw more light on this permittivity of free space. Epsilon naught, call it epsilon naught. Let me just clean this one up. Okay, so epsilon naught is actually, there's a value, is a constant. It is 8.85 times 10 raised to the power minus 12 Coulomb square Newton raised to the power 2, raised to the power minus 2, then meter raised to the power minus 2. Okay, no, this is minus 1, sorry. Okay, so this is the permittivity of free space. It's a constant. By the time you put this one inside K is equals to 1 over 4 pi epsilon naught. 1 is a constant, 4 is a constant, pi is also a constant, 3.142. Epsilon naught is a constant, this one. By the time you put all the values there, K in itself is 9 times 10 to the power 9. You understand? So that is what K is. That's what K is. Okay, so we are going to quickly take an example to buttress this. Okay, I have an example on the board. It says a charge Q1 is equals to 5.0 microfarad. This U here is micro Coulomb. Is placed 30 cm to the west of another charge Q2, which is 12 microcoulomb. What is the force exerted by the positive charge on the negative charge? So this kind of force is attraction because positive and negative are interacting. Okay, so solution. Let me just divide the board so I can have my solution. Solution. So by diagram, I have Q1 placed on the west. So Q1 is here and Q2 is here. Okay, so separation distance between the two of them is 30 cm. So I have 30 cm like this, separating the two of them, 30 cm. And Q1 has its own charge, 5 microcoulomb. Q2 has 12 microcoulomb. Okay, so it said what is the force of attraction between the two of them? All right, so Coulomb's law states that F is equals to K times K Q1 Q2 all over R squared. So what is K? We know that K is 9 times 10 to the power 9. The units of K is Newton meter square Coulomb square, like this. Okay, so I now say times, this is 5 times 10 to the power minus 6 Coulomb. Still times 12 times 10 to the power minus 6 Coulomb. Now this micro Coulomb is small, so it is to the power of minus 6, 10 to the power of minus 6. That's what you have there. So all this one, all over, separation distance is 30 cm. But because we are dealing with SI unit, we convert it to meters. So we know that 100 centimeters make 1 meter. So by the time you divide 30 cm by 100, you will get 0.3 meters, so all square. So I have the numerator, this is what I have a numerator on the top, and this is the denominator. So I can just simplify it like this. I say 9 times 10 to the power 9 times, let me remove all the units so that it will be simple. Then 5 times 10 to the power minus 6 times 12 times 10 to the power minus 6 all over 0.3 all square. So by the time you compute your calculator, the answer you will get is 6 newtons. F is equals to 6 newtons. So that's the force of attraction between these two. Okay, now take note of these units. These units, let me explain something about the unit system that we have here. Okay, take this one off. So in physics, if you are given a formula like this is F is equals to K Q1 Q2 all over R squared. And I want to get the unit of K. You know, we said that K is a constant. K is a constant. 9 times 10 to the power 9 Newton meter square Coulomb raised to the power minus 2. How did we get this unit? It's a derived unit. It's a derived unit. You have fundamental unit and you have derived unit. This is a derived. How do you get this derived unit? It is gotten from this formula already. This formula is the formula that has some parameters that already have their own units. So if I come to make K use the formula, because K is what we want to get. So I said F times R square is FR square. So I'm making K use the formula is equals to K Q1 Q2. Now F R square over Q1 Q2 is equals to K. Now by dimensioning, F is in Newton. You understand? R is in meters, so it's square. And charge is in Coulomb. So I have two charges, Coulomb and another Coulomb. This one is, I'm writing it like this so that I make it linear. This one is supposed to be under here, but if it comes up, it will take this in this format. So finally, I'm getting n m square and c raised to the power minus 2. So this is the unit for the k in that expression. Okay, so we'll go into the principle of superposition. Okay, so we have this on the board, superposition theory. We are going to be looking at the interactions between more than one charge system. You know, initially we looked at a certain force between two charges. So the question is that how do we now calculate if it's more than two charges? On the board we have interaction of three charges, Q1 and Q2 and Q3. So from what we know before, Q1 and Q2 are two charges on a straight line. Their force will go on this direction. So this is Q1 and Q2. The force coming here is the direction force 1, 2. That is coming as a result of these two charges interacting. Okay, and Q1 and Q3 will have this resultant force here acting on these two, either attraction or repulsion. So there is a central force in between the two of them, which is known as resultant force. This is the force that we will have to resolve. Either that this can be resolved by parallelogram law, or if they are on 90 degrees, you can resolve them using the Pythagorean's theory. Okay, so I'm going to give us a worked example of how this thing plays. Okay, so we have on the board a worked example. So this is the diagram of three charges interacting. This is one of the charge here, this point, and this point. This Q1 is minus 1.0 microcoulomb, Q2 is plus 2.0 microcoulomb, and Q3 is plus 4.0 microcoulomb. Say, find the electrostatic force Q1, that is this force on Q1, okay, to the two other charges. So Q1 is to this side and Q2 is to this side. Q1 is to Q1 is to Q2 and Q1 is to Q3. So you see, from the normal definition of Coulomb law, these two charges will have expressed a force F12, and these two charges express a force F13. But because these two charges are at right angle, we will now find the resultant. The resultant is F1. The resultant is F1. So we should express your result in magnitude and direction. So our task is to find F1. So from Coulomb's law, we know that F12, remember, F12 is equals to K. K is always constant. Q1, Q2 all over R squared. Do we have distance here in this question? I think I have distance here. Let me see whether the diagram have a distance. Yes, it does. I didn't include it. So the distance here is 10 cm here, 10 cm, and here is 20 cm. Okay. So F12 is given like this. So F12 is equals to K is 9 times 10 to the power 10. First of all, and Q1 is given as, I'll just remove the units. I don't need the units so that I don't get it complex. 1.0, that's minus 1.0 times 10 to the power minus 6. Why? Because it's a microcoulomb. Then times 2.0 times 10 to the power minus 6 all over. Now this 10 cm is to meters is 0.1 meter. So 0.1 meter all square. So this is F12. So F12 is given as 1.8 Newton. 1.8 Newton. So it's attractive. It's attractive to the positive x direction. Mind you, this minus here it will not affect the calculation. It just shows you what the direction is. So we have gotten F12 already. Now I'm going to get F13. F13, the same thing, K times Q1 and Q3. So we are dealing with Q1 and Q3 all over R squared. So F13 is equals to K is already a constant. All right, that's K. Q1 is minus 1.0 times 10 to the power minus 6, and Q3 is 4 times 10 to the power minus 6 all over R squared. This R is 20 cm. 20 cm to meter is 0.2 meter all squared. By the time you compute with your calculator, what you'll be getting is minus 0.9. Okay, not minus 0.9 Newton. 0.9 Newton. So this is the positive x direction as well. But like I said, you see, this thing now is going this way, this thing is going this way. That's what we need to know. These two forces are perpendicular according to the diagram. Understand? So I'm going to draw a new diagram using only the force that we have gotten. I'll quickly draw it here and I'll transfer it up. So I have F12 is going this way. So F12 force is 1.8 Newton and F13 force is 0.9 Newton. So our task is to find this one, F1, understand? F1. So if I continue the line like this, this is this side and this is this side. So to get the resultant is just to look for the Pythagorean, using Pythagorean theory, I can get the hypotenuse. So let me remove this one. Let me remove this one so I can continue up there. I'll remove this one as well. I've gotten what I need. So it's just for me to get the okay, so by Pythagoras theorem. So I have the resultant F1 is equals to big square root of 1.8 square plus 0.9 square. That's the resultant, how it's going to be like. So by the time I am done with it, I'm going to be getting 2.01 Newton. You understand? So, but the angle is making on this axis is actually tan inverse, that is, of this relationship. So, therefore, the angle is equals to tan inverse of 1.8 over 0.9. 1.8 over 0.9. So, actually, that is 2. Tan inverse of 2. Theta will give us 63.5. 63.5 degree. So, this is the direction. So you say express your results in magnitude. This is the magnitude, and this is the direction. So it's as simple as that. Using superposition theory, we can get the resultant of force that are more than 2 charges involved. Okay, so I have on the board the electric field. So an electric field is a region where electric charge experiences a force. Just like a football field, it's an area where we play match. So if you have a small unit positive charge Q placed at any point in an electric field, it will experience a force of F. Okay, so that the field strength E, also called E field, at that point is defined as E is equals to F over Q. That is force on the unit charge. So force can be made of the formula. I have electric field times the charge. Okay, so the magnitude of the E is the force, that is E, is the force per unit charge, So that's the definition, force per unit charge. And the units are simple, is force NC or NC minus 1. That's the units of electric field. Okay. So there's a relationship between electric field and Coulomb's law. We know that electric field is defined as force per unit charge, But force is known as K, Q1, Q2. If Q1 and Q2 are similar, it's Q squared over R. Understand? So if I have this relationship, this is equation 1 for electric field, equation 2 for the relationship between force and the charges. I can now say substitute 2, equation 2 in equation 1. I can do that. So when I do that, I now have E, electric field. Then this is force, F is force. So I just put everything that is in there. K, Q, Q1, Q2 over R squared. That's for force. Then times 1 over Q. Remember, this one is the same thing as saying, this is force all over this one. So this charge can cancel one of the charge here. So I have E is equals to KQ over R. So this is the relationship that came from between electric field intensity and the Coulomb's law. So like I said, this is measured in Newton per Coulomb. So if you are given a question to calculate the electric field on a charge, you understand, just to use the same K constant of potentiality and the distance from where the charge is to the point where you are considering. Okay, so I have a question on the board that is on electric field. It says a point charge of Q is equals to minus 2.0 times 10 to the power minus 6 Coulomb is located in space. What is the magnitude and direction of the electric field at point 0.3 meters away from the charge? So take K as this. So the electric field E due to point charge is given like this. E is equals to K is a constant, then this is the charge all over R squared. Okay, so where E is what? The electric field. Remember we derived this in the previous video. So electric field, strength, you can call it field strength or intensity, electric field strength. And K is 9 times 10 to the power 9, that's the constant of polarity. Okay, Q is the quantity of charge in Coulomb, quantity of charge in Coulomb, and R is the distance of separation in meters. Okay, so distance from the charge, yes, in meters. So by the time I plug in everything I have here, E is equals to, what is K? 10 times 10 to the power 9 times, what is the charge? The charge is 2.0 times 10 to the power minus 6 all over 0.3 all square. 0.3 all square. There's a minus here, but I said that minus is for direction. It's not for, it doesn't affect the formula or the calculation. So by the time I use my calculator to compute this, what I'll be getting is 2 times 10 to the power 5 Newton meter. Newton Coulomb, sorry. Newton Coulomb. Okay, so that's the final answer. That's the final answer. But the negative charge that is here, it's just telling us that the electric field points towards that negative charge. You understand? It points towards the charge. So since the charge is negative, it points towards the charge. So this is the answer for this particular question. So we'll try to wrap up this course by looking at field lines, electric field line. So a line of force is just what you use in showing direction. So a point charge will show lines of force radiating away from that point charge. So if I have positive charge, for instance, just like this, so the line of force will radiate out of it like this. So you see direction, that signs like this, you understand, for a point charge. So if you have a positive and negative charge interacting, this positive charge and this negative charge, we say like or like charge attract. So you see that the lines of force will go like this, we go like this, we go like this, we go like this. So there's an attraction. Understand that some of them will go because there's no field of influence around it. So it's just showing us the direction of the lines of force. If it's actually repulsion, if there are two charges that are like, you see that there's a repulsion like this, repulsion. So there are two lines of force, attraction and repulsion. So in summary, there are only two types of electric charge, and they are habitually called the positive charge and the negative charge. Like charges repel and unlike charges attract each other. Unit of charge is Coulomb. We saw in this video that charge is always conserved. That is, the algebraic sum of the charges is in a closed system does not change. We also saw that electric charge is quantized, occurring only in discrete amounts. We talked about the force of attraction between or repulsion between two charges is given as F is equals to K Q1 Q2 all over R squared, and we saw electric field is given as K Q over R squared. So there's a relationship between the two of them. Why electric field is vector? Electric field is a vector quantity, yes. Okay, so finally we saw the lines of force. Lines of force are only a visual way of representing an electric field, like as we have on the board, showing direction and showing whether they are attracting or repelling. I hope this video has been informative for you. I'd like to thank you for viewing.